Okay, so we have reached the last chapter of this course, our college algebra course. So we're in chapter 7, and in chapter 7, we're just going to look at some separate topics in chapter 7. So we're going to look at the 4 sections of this book. Section 1, we're going to look at sequences and series, then followed by sections 2, 3, and 4. So let's take a look at section 7.1. In section 7.1, we're looking at sequences and series. So I have here, I've copied from the book the definitions because the font set looks nicer than my handwriting. So a sequence is simply a function, just like your ordinary functions you worked throughout the course. The only difference is that with a sequence, this function's domain is the set of natural numbers. Remember, the set of natural numbers are your counting numbers. These are 1, 2, 3, and so on, all the way on up to n. So that's what's different in a sequence versus an ordinary function whose domain is allowed to be all real numbers or anything within the domain, but the restriction of natural or counting numbers for domain is not there. So those are ordinary functions, but this time we're talking about sequences. Now, for example, if you look at this line, this is an example of a linear function, right? We've seen this many times over. So this is f of x equal 2x. And if you look at the domain, look at the x-axis. Notice x could take on any value, any real number over the entire number line. So this would be just an ordinary linear function whose domain is the set of all real numbers. Now we can create a sequence corresponding to f of x equal 2x. That's right next to it. But if you look at the graph now, notice you see these gaps between the dots, between also on the x-axis, or I'm sorry, now the x-axis is the n-axis. This is just to remind us that the set is the set of natural numbers, the counting numbers. So we no longer, for instance, allow for numbers like 1.4, 1.5, 2.7, things like that. So the domain of f of n equals 2n is going to be 1, 2, 3, 4, 5, and so on. And then, of course, you plug those numbers in. For instance, when n is 1, 2 times 1 is 2. So you get the first dot at a height of 2. The next dot that's when n is 2. 2 times 2 is 4. So that would be the next dot. Now, as far as the notation is concerned, by the way, because different textbooks, different authors have different notations. And one thing that I can do here is I can write different notations for a function. So for instance, in the book we're using, the author uses a sub n. Okay, let me hold on. Sorry, hold on. All right, so I can use the function notation here, like the book has. I can write a sub n equals 2n. Remember, the unrestricted domain f of x is 2x. So now it's going to become n. Now, some textbooks also use the brace notation. We can write it like that. Some also use f to maintain the general structure of a function, and instead of x, we have f of n. So these are some of the variations in writing the sequence. Okay, and now, for instance, if you look at this one right next to the one I just looked at, look at this one. For this one, this is a sequence 1 over n. And again, n always starts with 1, 2, 3, 4, and so forth. The unrestricted version of this example would be like f of x equals 1 over x, wouldn't it? So that would be the unrestricted version of the function. And we know what the graph of this function looks like. So if I'm to draw actually f of x equal 1 over x, it's going to look like this, isn't it? It's going to go over through, actually, all these points will be on that function. So that's just 1 over x, right? And we've seen the graph of that before. But the difference now is what you're seeing here is that we only look at whole numbers. Okay. And we're going to look at the examples in just a moment here. Now, anytime we add up the terms of a sequence, the result's going to be a series. So let me hold off on the series here until we actually look at some example of sequences first. All right. So let's take a look at some examples. So in this example that we're going to look at, let's say we want to write the first 5 terms of a sequence. Okay, now the sequence that I have in mind is this sequence. Suppose my sequence is a sub n equals 4n plus 10. Notice we're using the n notation now. So the first 5 terms, that's what we want to do. What are the first 5 terms of this sequence? Now, the terms of the sequence, by the way, the first term is going to be a sub 1. The second term is going to be a sub 2, a sub 3, and then so on and so forth. So in general, a sub n. If there is finite number of terms such as the one I have, then this sequence is called a finite sequence, because the number of terms can be counted. There we go, finite sequence, because they have a countable number of terms. If the sequence goes on indefinitely because the set of natural numbers is infinite, so here's your nth term, and then it just keeps going on forever, then this sequence is going to be an infinite sequence. Okay, so that's just the types. So let's write out the terms of this sequence. So a sub 1, that's when n is 1. It's going to be 4 times 1, because 4n means 4 times n. 4 times 1 plus 10, and that's going to be 4 plus 10, 14. That's the first term. For second term, n is now 2. So we're going to go 4 times 2 plus 10. And that's going to be 8 plus 10, or 18. And a sub 3. So you kind of see how this goes. It kind of forms a pattern, right? And one thing that's interesting about sequences and series is the patterns that we see in these expressions. That's 12 plus 10, or 22. And you can see that these values are separated by a fixed constant, namely 4. So let's do just 2 more to finish this off. So it's going to be 4 times 4 plus 10. That's going to be 16 plus 10, or 26. And a sub 5 would be the last one, 4 times 5 plus 10. And that's going to be 20, and there you go. Just wanted to write the first 5 terms. Again, each term is separated by 4. So writing it in the form a1, comma, a2, a3, a4, and a5. The numbers are 14, 18, 22, 26, and 30. Okay, so that's what that example is for. Okay, let's take a look at another example. So for instance, in this other example now, suppose I have a sub n is equal to n plus 5 over n plus 4. Something like this one. And again, we're just going to plug in for the expression 1 plus 5 over 1 plus 4. So that's going to be 6/5. A sub 2 is going to be 2 plus 5, 2 plus 4. That's 7/6. So you kind of see how this is going to go, right? A1 is 6/5. A2 is 7/6. So it looks like in each case, I'm adding 1 more to the numerator. Next one is going to be 8, adding 1 more to the denominator. A sub 4 is going to be 9/8, and a sub 5 is going to be 10/9. I'm just following the pattern that I see from term to term. Okay, and there you have that. Now, let's do another example. Let's say we want to know whether a sequence is finite or infinite. So for instance, let's say I make up this sequence. Suppose I'm looking at the sequence of natural numbers themselves. 1, 2, 3, 4, and 5. So for this one, again, we want to decide whether each sequence is finite or infinite. The fact that the term ends with 5, that means there are 5 terms. It terminates, there are no dot dot dots in the end. The trailing dot dot dots tells me that this is a finite sequence. So we're going to write this one as finite. Okay. And now the same sequence, suppose it was 1, 2, 3, 4, 5, comma, dot, dot, dot. Again, that means this goes on forever. So this would be now an infinite sequence. Okay, so pretty straightforward. Now, let's talk about a series here. Okay, so I'm just going to grab this right in here. Let me bring this up. And here is the series now. Anytime we add the terms of a sequence, the result's going to be series. Now, if the sequence is finite, notice it ends with the nth term. That's what we call this, a sub n. It's called the nth term of the sequence. So if it ends with a sub n, then that means we have a finite series, the sum of those. See, you add the terms, sum of the terms of a sequence, the result's called a series. Now, if the sequence is infinite, the key is the dot dot dots, then the series that it generates is called an infinite series. Now, if you look at the upper, what we call the upper limit of summation here, this one is n, and for the infinite sequence, that's the infinity symbol that you're looking at there. Okay, so that's going to be infinity. So let's see now how we can work with the series here. Okay, now every series, and by the way, we can write series in what we call the expanded form. That's what you're looking at here. Or we can write it in a more concise form in sigma notation, which is what's to the right of equal sign here. Okay, so let's take a look at sigma here. Sigma is a mathematical operator. There you go. There are 2 sigmas. It's actually a Greek letter in a Greek alphabet, sigma is. There are 2 sigmas in Greek alphabet. One is the one that you're looking at. The other one is this sigma. And this sigma has different interpretation in physical sciences and in statistics and in other fields of STEM. So, for example, sigma in statistics stands this one. The little lowercase sigma stands for population standard deviation. In physical sciences, for example, the sigma could mean density function. So again, a lot of different interpretations depending on the field, but we're not going to look at this sigma. We're focusing on this sigma. The capital sigma, if you will, this is a mathematical operator. Okay, so how does this operate, this mathematical operator? This mathematical operator operates on the series. So let me show you how. Okay, so for example, let's say I have an expression that looks like the following. I have the sigma of I equals 1 to n of a sub I. I'm looking at what we stated up here in the beginning, the definition of a finite series. Now, every sigma operator has a lower index, what we call, or first of all, it has an index, forget the lower, it has an index. Now we use I, some books use J, sometimes it's K. It really, that letter is a dummy letter. It could be I, J, K, L, M, N, O, P, whatever. But it's called the index of summation. And then the index usually starts with 1, sometimes with 0, even sometimes you may see, ironically, negative integers, although we define them over the set of natural numbers. But we're going to stay focused on natural numbers in this lecture. So for us, it's going to start from 1. It could start, however, at another location. I'll show you one in a moment. But let's say it starts at 1. The 1 is called the lower limit of summation. The n is called the upper limit of summation. So every sigma has a lower limit and an upper limit. So how does this work? We always start with the lower limit, that is 1. And we're going to replace I with 1 the first time around. Okay, so once we change I to 1, the subscript looks like A sub 1, and that's this term. Now, the way this operator works, the mere presence of sigma is a command to add. A command to add. So next we're going to add y. That's how this operator operates. Okay, so we're going to add. Remember, we started with 1. So next time we add, what are we going to add? Well, we're going to increment, meaning increase I from 1 by 1 more. So it's now 2. And we always increment by 1, folks. We never increment by half, by pi, by any other number, by 2, by 4. The increment of the index is always by 1, as you always increase. Okay, you don't decrease. So I have A sub 1, A sub 2. Next time around, I have A sub 3, A sub 4, A sub 5, and so on. Well, how far is this going to go? Well, it's going to go as high as the upper limit. So whatever the upper limit is, we're just going to actually count the upper limit, and that's where we stop. So there you go. That is how a sigma operates. Okay, so again, it's a very efficient way of writing these formulas. Now, for instance, let's take a look at an example here. Let's say in this example, I want to do sum, and I'm just going to play around here, change the index from I to k. Okay, just to show you the index doesn't have to be I. And also, by the way, here I does not equal square root of -1. So please do not think that this is the imaginary unit. It's just a counter. That's all it is. A dummy variable, they call it. And let's say I'm going to go make something up here. Let's say I have my expression in front of sigma is going to be -1 to the k times k. And that's what usually happens. You typically have sigma, and then you have some algebraic expression in front. And I equals 1 to whatever, let's say n. That algebraic expression is what sigma operates on. Okay, so this is the expression that I have. Now, how's this going to work out? Well, we start with k equals 1. So S means sum. Remember, the result of sigma is the total, a sum. So we're going to start with k1, that's -1 to 1 times 1, and then we add. Then k is incremented to 2, so it's now -1 squared times 2. And so on, and so forth. So it's going to be -1 to the 4th times 4, -1 to the 5th times 5, and finally we go -1 to the 6th times 6, and we stop. You see that once we reach the upper limit, that's the sign to stop. And then we actually do the arithmetic now. Remember, -1 to odd powers would be -1, and to even powers is going to be 2. So I'm just going to write this thing out. It's going to be -1. Next one, -1 squared is this one. -1 squared is 1. 1 times 2 is going to be 2. Next one, -1 cubed is going to be -3. The next one is going to be +4, -5, +6. So you see the pattern. This is what we call an alternating series. So where we have the patterns starting with negative and then followed by positive, followed by negative, and so on. The alternating pattern could start, for example, it could be 5 minus 6 plus 7 minus 8. So we could start with positive, then negative, then positive, or as you see, it can be negative, positive, negative. As long as they alternate, that's what these are called, alternating series. Now, of course, we can always add the numbers, right? So for example, on the plus side, I have 6, 4, 2, that's 12. On the negative side, we have negative 9. So the result of this series is 3. And there you have that one. Okay, so we say that we have evaluated this series. Okay, let's take a look at something else now. How about one more example? Let's say in this next example, we're going to look at sigma. I'm going to go I, just like the book does again. Remember, I, J, K doesn't matter. I 1 to 5 of this time. Let's go 3 to the I minus 4. So remember, I starts with 1. So here it goes. 3 to the first minus 4. And then we add. Then we go 3 squared minus 4. And then add. 3 cubed minus 4. Add. 3 to the fourth minus 4. Add. And finally, 3 to the fifth minus 4. And for this one, 3 minus 4, that's negative 1. 3 squared is 9 minus 4, 5. 3 cubed, 27. 27 minus 4 is 23. Next one, 3 to the fourth is 81. 81 take away 4 would be 77. It's going to be plus 77. And finally, negative, 3 to the fifth, that's going to be what, 243, all right, because that's like 9 times 27. 3 squared, 3 cubed, 180, 63, yeah, 243. Please verify, I think that's right. And 243 subtract 4, it's going to be 239. And then we can add them up, and whatever this number turns out to be, let's see, that's 100. And that makes it 339, and this is 4. And again, please verify my arithmetic because I'm not using a calculator. And that's what I got. Okay, and there is the result of this sigma. So it's pretty easy to work with the sigmas to expand them. All right, now let's take a look at another example. So in this next example, what we want to do is this. Let's say, for instance, this time I'm going to give you some of the values for like x sub 1, x sub 2, like that. So suppose, let's say x sub 1 is negative 2, and let's make x sub 2 negative 1, and x sub 3, we'll make that 0. Okay, so that's what those numbers are. These could be 3 scores on something. And suppose we want to do this. Let's say we want to evaluate the sum I1 to 3 of this expression, 3x sub I minus x sub I quantity squared. So let's see how this is going to work out. Now for this one again, if we write this series out, remember you start with index at 1. So the first expression is 3x sub 1 minus x sub 1 squared. And then plus 3x sub 2 minus x sub 2 squared. And then plus 3x sub 3 minus x sub 3 squared, right? But then we know the values of x sub 1, 2, and 3. Let's plug them in. And the first one is going to be 3 times negative 2 minus x sub 1 is negative 2, but then it gets squared, so I'm squaring that. So that's the first expression. Plus, how about the second expression? 3 times x sub 2 is negative 1 minus negative 1 squared. Plus x sub 3 is 0. That's 3 times 0, negative 0 quantity squared. Okay. And let's start with the first set of parentheses. 3 times negative 2, that's negative 6. Double negative on 2 makes positive 2. We square it. Okay, and then next to that, 3 times negative 1 is negative 3. And negative 1 squared is positive 1. Negative in front of that makes it negative 1. Okay, so we got that one. Let me make sure. Okay, sorry. The way I worked it is incorrect. See what a difference it makes. Let's do the order of operation. We're looking at PEMDAS, parentheses, exponent, and so on and so forth. So let's do negative 2 squared. That is a 4. 4 positive. Negative in front keeps it negative. Ooh, good thing I caught that one, huh? I'm sure a lot of you are saying, whoa, wait a minute. You didn't do that right. So there you go. 3 times negative 2 and negative 2 squared 4. Negative of that. Next expression, negative 1 squared is 1 minus 1. That looks right. And the last one is 0. There you have it. So how is this going to work out? The first sum is negative 10, then negative 4. The whole thing is negative 14. And we are good with this one. So you see how that works. Okay. Now, the next thing we're going to look at is the following. We're going to actually look at some of the properties of summation. Okay, there's not too many properties per se, but we're going to look at these. So if we do have a sequence, right, if we have a sequence of A1, A2 through AN, and then a second sequence, B1, B2 through Bn. So we have 2 sequences. And this time C, the C that you see here, the C that you see, that one is a constant. C for constant. Now, with that, part A of the summation properties says that if you sum a constant from 1 to n, the result is n times a constant. So to give you a quick example of this one, let's say I want to do sum 1 to 3 of 5. You see, 5 is the constant here. The C that you see, the C that's in here, that's 5. So first of all, let's write this out, see what this says. Remember, we start with the expression that's in front of the sigma. When I is 1, that's 5. Because notice 5 does not depend on I. It's a constant. So when I is 1, you just simply write 5. And then you add. Increment I from 1 to 2, but then 5 doesn't change. You add. Change I to 3. Again, 5 doesn't change. You add another 5. So it looks like you have 3 5s, right? 3 times 5. But then 3 is the upper limit, isn't it? This is the C and this is the N in this formula NC. N is the upper limit of the summation. And here's n. And C is the constant that's in front of the summation. So according to this formula, part A, I could have just multiplied 3 times 5 instead of writing it out. Okay. Now part B, in part B, we're allowed to bring a constant outside of the summation. That's what this one says. So to give you an example of this one, suppose I want to do sigma of 1/2 x sub I. I goes from 1 to 4. For this one, I can bring the 1/2 outside the summation and simply do sigma of x sub I. I goes from 1 to 4. And what does that mean? Again, I is 1, so it's x1. I becomes 2. I becomes 3. I becomes 4. There you go. So that's what that expression means. So it is okay to bring out a constant. Now note, we can only bring out a constant in front of the sigma, not variables. The next one, part C of this one, tells us that if you add And part C and D I usually write together. To add or subtract two series, you can add, subtract individually. Okay, so the sum of A plus B is sigma A plus sigma B. And so let's take a look at an example here, see how this is going to work out. Okay, I'm going to try this example. Okay, and let me move this one away. We'll look at this property of summation later. So in this example that I'm making up, suppose I have the sigma I from 1 to 4. Okay, that's the sum from 1 to 4 of, and suppose I want to go, let's say parentheses 3i squared, and then plus 2i minus 4. Okay, and let's say that's what I want to evaluate using the properties we know so far. So because I have, this is in the form, by the way, of sigma of AI plus BI, right? Two series, and if you want, you can go plus CI. So I can view this as the sum of three series. The CI here, of course, is a constant, a series of a constant number. So let's see. The part that I can use right now is the following. I can write this as 3 sigma of I squared, I from 1 to 4, plus, see, I'm doing the addition rule, plus the sum, I goes from 1 to 4, of, bring the 2 outside of just I. See that 2i? I can bring 2 outside, and I did. It is now on the outside. There is the 2. And then, of course, negative the sum of a constant 4. I goes from 1 to 4. So this is how I can rewrite it. Okay. Now, let's want to evaluate this. One way to evaluate it is to do this. We actually write them out. Let's write out this one. That one says 3 times 1 squared plus 2 squared plus 3 squared plus 4 squared, right? The one next to it, this one, is 2 times sum of the i's. I goes from 1 to 4. So this one is like 1 plus 2 plus 3 plus 4. And finally, the last one, negative 4, sum of 4, negative sigma or sum of 4. I can write that as 4 plus 4 plus 4 plus 4. 4 times, right? Okay, and then I can work the arithmetic here. So what do we get? We get 1 plus 4 plus 9 plus 16. Inside parentheses, 2 times 1 plus 2 plus 3 plus 4. That's 10. And the last parentheses, I have 4 4s, so that's 16. The first of the parentheses, that's 20, 30. 30 times 3 is 90 plus 20 minus 16. So it's going to be, looks like 94 if I did my arithmetic right. So notice we did it, it worked. Takes a while, but that's what it is. We can also now use properties of summation, other properties of summations to do this. And that's where these other ones come into play. Okay, now the formulas that you're looking at, by the way, these formulas, I'm just going to say in calculus, you will see these formulas again, depending on the calculus you take. But usually you will see this in a calculus course. You will see exact same series again. Now, let's redo this example using the properties. So what properties am I talking about? Well, the one property that we had was in the beginning. Remember this one? Sum of the constant is n times the constant. Okay. We can apply that to the last sigma. Okay, so let me write the pieces here. Sigma of 4, I goes from 1 to 4, is 4 times 4. That's this 4. This is the other 4, or 16. Okay, and that's precisely what this was. Now, let's look at sigma of I. So sigma of I goes from 1 to 4. According to this formula, the sigma of I from 1 to n, which means 1 plus 2 all the way up to n, looks like this is the sum of the first n natural numbers. The series is. This one, the formula says you can write it as n times n plus 1 over 2, where n is the upper limit. So this is going to be written as 4 times 4 plus 1 divided by 2. In parentheses, I have 5. 4 halves is 2. 2 times 5 is 10. And there you have that one. Notice that's the 10 that we saw up here. Okay. And let's do one more using this summation properties or rules, they call them. What about sigma of I squared? I goes from 1 to 4. Now I'm looking at this formula. The sigma is going to be n. N is 4. Remember, n is the upper limit. That's n. So it's going to be 4 times 4 plus 1 times 2 times 4 plus 1 divided by 6. All right. Now, how is this going to work out? This is going to equal to 4 times 5 times 2 times 4, 8 plus 1 is 9 divided by 6. I can write 4 as 2 by 2, 9 as 3 by 3. Then I can divide by 6. One of the 2's and one of the 3's on top multiply to 6, cancels with the bottom. So this is going to be 30. And that's what we saw again here. That's the 30 we saw. Okay, now I can actually redo this example using the properties of sigmas. So call S the sum. We already have the answer, by the way, folks. The answer is 94. But I just want to use the properties to show you how these summation rules work. So that's 3 times the sigma of I squared. We did that one. That one turned out to be 30 right in here. True? That's the sigma of I squared. We did that one again. Now, what's next to that? Next to that is 2 sigma I. And it's going to be plus 2 and sigma I. Sigma I is 10 right in here. That's 2 times 10. And what else? Finally, we have negative sigma of 4 from 1 to 4. We did that one. Sigma of 4 from 1 to 4 is 16. So it's negative, just that sigma. That's negative 16. Now you look at this, we're going to get what? 90 plus 20 minus 16, which is exactly what we have up here. So this answer, just like before, is going to be 94. So what I did, in fact, was use the properties of summation in order to simplify this. If n is small, it's not worth maybe the hassle, but for n large, check out this example. Let's say I want to find the sum of the counting numbers, that's I, from 1 to 1,000. How about that? If I want to do this on a calculator, let's say I got to do 1 plus 2 plus 3 plus 4 plus ... plus 1,000, don't I? It's going to take me a long time, room for error, and that's really not how we want to do it. So instead, I'm going to use the formula. N is 1,000, and I'm looking at this formula. So the sum is going to be 1,000 times 1,001 divided by 2, isn't it? That's going to be the total of the first 1,000 counting numbers. 1,000 by 2 is 500. So what is this going to be, this total? It's going to be 500 times what you're looking at, times 1,001. 1,000 times 500 is 500,000. 500 times 1 is 500. So the answer is 500, 500. There you go. Much faster, probably more accurate than if I did on a calculator and I still be punching the numbers in. And there you have that example. So again, as you can see, these sigmas are very powerful. And so I'm going to stop here. Hopefully you followed everything that we have done. And we're going to be using these now in our next sections, next two sections. In fact, when we talk about arithmetic and geometric sequences and series. So we are done with the video for section 7.1. Thank you for your attention.